Hey! Welcome back to my channel. For a very long time, humans have imagined what life may be like in other worlds. Thanks to the James Webb Space Telescope, the most powerful telescope in existence, that question can finally be answered. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed some peculiar anomalies from one of the planets in the system, Proxima b. These anomalies, called artificial lights, have puzzled the best minds in the scientific community. But what are they? Do these lights suggest the existence of intelligent life on the planet? Join us as we explore James Webb's terrifying discovery of city lights that changes everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. The non-profit's objective is to gather spaceborne radio signals. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. However, in the past 30 years, no verifiable alien signal has been discovered. After that, the James Webb Space Telescope's successful launch aided in the quest to examine a range of distant undiscovered planets orbiting far-off stars. The largest telescope in the world, floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, will be used. 20 years ago, there were no known planets outside those in our solar system. Since then, more than 4,000 exoplanets have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. The Galileo spacecraft turned its equipment back toward Earth en route to Jupiter and found a definite indication of the presence of plants. The instrument detected the vegetation red edge, VRE, biosignature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth that is covered in a jungle should have a strong and easy-to-detect VRE signal. The JWST will measure the VRE of far-off Earth-like planets in the habitable zone around stars. They could be important signs of life in the exoplanet atmosphere. When sunlight crosses a planet star, the JWST may be able to detect it as it enters its atmosphere. The missing wavelengths would then be discovered via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method may be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres similar to our own, with a predominance of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't usually present, one may be able to detect technological life. Chlorofluorocarbons, CFCs, generated for use in refrigeration and cleaning products would probably be noticeable to aliens monitoring Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, that would be a clear indication of civilization. Actually, life on exoplanets might not even remotely resemble life on Earth. Sometimes, even earthly life, like extremophiles, species that can endure in environments where other living things would perish, can seem alien. This is a group of organisms, primarily bacteria, that can withstand extreme conditions. Some humans can withstand heat up to 250 degrees Fahrenheit, while others can survive in strong acids with pH levels below 3. Since planets like Earth are more likely to support life than planets with severe temperatures or acidic conditions, it could be a good idea to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are less common and typically have shorter lives. However, in our universe, the likelihood of studying planets orbiting around red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. There is more time for the formation of life and evolution to produce complex life forms because these stars have longer lifespans. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone might have liquid water on their surfaces. The TRAPPIST-1 star, despite having a much smaller and colder mass than our Sun, radiates light that is similar to that of Earth. Due to the close orbit of its planets, the best chance for humans to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our nearest star. Proxima is about 600 times fainter than the Sun, so a planet must be 20 times closer to it than Earth is to the Sun in order for it to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, a Goldilocks-like habitable zone where the light intensity is just right to melt water. Proxima b circles Proxima Centauri. It's possible that Proxima b is an airless, lifeless planet, given that it orbits its red dwarf star, Proxima Centauri, at a distance of only 4.6 million miles. The planet Proxima b is in a close orbit that exposes it to strong solar winds that can completely destroy its atmosphere. It also provides enough sunlight for temperatures and liquid water similar to those on Earth. Because of its close proximity to the star, Proxima b is thought to be tidally locked, always showing the same side to the star, as the Moon does in reference to Earth. Proxima Centauri is about 1/8 the mass of the Sun and burns far less brightly than one might anticipate for a planet so near to its star, just 5% of the Earth-Sun distance, which may be anticipated to be a red-hot cinder. Liquid water could easily exist on Proxima b as long as the planet has an atmosphere to hold heat in. Since the total energy reaching it from the Sun is only 65% of what Earth receives, however, the planet is not especially friendly to life. It is most likely tidally locked, which means that it always faces the same direction toward the star, producing permanent day and night sides with significant temperature changes. The planet also receives 100 times as much high-energy radiation as Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima b is also bombarded with high-energy particles during star flare-ups. Unless it has a shielding magnetic field similar to Earth's, there are certain realistic conditions that could make it a pleasant world. Sadly, models suggest that the atmosphere of tidally locked planets may be susceptible to rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Because we don't know anything about Proxima b's volcanic activity or magnetic field strength, we can't even guess whether or not the planet has an atmosphere. But since an atmosphere presupposes the existence of seas, and the two taken together presuppose the existence of life, we are desperate to know if Proxima b has a sophisticated civilization. It might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima b has triggered a race to determine if it crosses its star's face as seen from Earth. These transits would let scientists determine the planet's size and mass, which would then enable them to determine its density, validating the planet's rocky makeup and providing information on the materials used to create those rocks. During a transit, starlight might disclose the nature of the planet by passing through its atmosphere, but the likelihood that the orbit will be in the right alignment for scientists to see a transit is merely 1.5%. The star's propensity to flare also complicates matters. Astronomer David Kipping of Columbia University says the star is tricky. A star's heat causes a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. Additionally, the James Webb Space Telescope was created specifically to study infrared light. Proxima b's infrared heat signature is the key to identifying the planet's atmosphere. Additionally, the infrared portion of the spectrum has a strong affinity for Hubble's successor, possibly permanently. The James Webb Space Telescope will be able to observe city lights on Proxima b's night side even if they were as faint as what our civilization currently employs on the night side of Earth. Webb could detect artificial illumination as long as it was constrained to a frequency band that is 1,000 times narrower than the starlight. Proxima b's day side is heavily coated with solar panels because of its unique spectral edge's ability to reflect starlight. As Proxima b revolves around its star, day and night are identical, with cool evening lows following daytime highs. The difference in temperature between day and night, however, depends on whether or not the planet is entirely composed of bare rock, as an atmosphere and ocean both conduct heat. In other words, if there isn't an atmosphere, Proxima B's day side and night side temperatures will differ more. In fact, since the day side will re-emit all of the energy it receives from Proxima Centauri as a black body, we can calculate the precise amount of black body radiation that should be present on the night side. On the other hand, the night side will look like a frozen form of hell. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, it will only take the JWST 11.2 Earth days to measure the IR radiation from Proxima B's two faces after it has successfully completed its orbit around the star. In the event that Proxima B has an atmosphere, the next step will be to analyze its makeup. The presence of gases like oxygen, water vapor, and methane in particular could indicate the existence of habitable circumstances, if not actual living things. To accomplish this, however, we must successfully capture starlight as it bounces off or travels through the planet's atmosphere, which is a very difficult task. However, Webb can only closely examine a few of the closest potentially habitable worlds because it was not built to look for extraterrestrial life. Additionally, it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. Webb is unable to detect the presence of unbonded oxygen, which is the strongest sign of life. Even if some mixtures of these gases may be suggestive of life, one of the planned ground-based observatories that will be able to conduct a thorough atmospheric investigation is the extremely large telescope, scheduled to begin operation in the middle of the 2020s. Ozone may be among the substances that the JWST is capable of detecting. Until those telescopes are operational, the JWST may provide information that we can consider for a decade in the future. Even more powerful space telescopes may employ cutting-edge techniques to conceal the blinding brilliance of a planet's host star and reveal starlight reflected back from the planet, considering doing something akin to covering the lights with your hand to improve your ability to see distant objects. Future space telescopes might do this by using small internal masks or large outside umbrella-shaped satellites. After starlight is blocked, studying light reflecting off a planet is much easier. Unfortunately, the majority of gas produced by terrestrial life can also be produced by non-biological factors. Methane is a gas that both cows and volcanoes release, and sunlight does this as well, converting water molecules into oxygen and hydrogen through photosynthesis. When searching for alien life, astronomers are sure to come across some false positives. Astronomers must have a thorough understanding of a planet of interest to assess if its geologic or atmospheric processes potentially resemble a biosignature and help rule out false positives. The next wave of exoplanet research may produce the compelling evidence required to establish the reality of life. The James Webb Space Telescope's preliminary data gives us a preview of the significant advancements to come. If there is life elsewhere in the cosmos, it is one of science's most pressing questions. It's possible that life is abundant throughout the cosmos, or it's also possible that we are completely alone and trapped on a solitary planet in deep space. In either scenario, significant philosophical or psychological adjustments are